Imagine a cat, a creature of curiosity and grace, lounging comfortably in a box. Simple enough, right? A cat in a box, a scene of innocence and simplicity. Now imagine this box is designed to isolate the cat completely from the outside world. No peeking, no interference. Inside this box, there's a tiny bit of radioactive material, almost invisible to the naked eye. This material has a 50-50 chance of decaying within an hour. Time ticks away and the outcome is uncertain. If the material decays, it triggers a mechanism that releases a deadly poison, a silent and unseen threat. If it doesn't decay, the cat continues to live, blissfully unaware of the danger it narrowly escaped. You close the box and wait for an hour, the fate of the cat hanging in the balance. Here's the question that boggles the mind. Is the cat alive, dead, or somehow both at the same time? This is the essence of Schrödinger's cat, a thought experiment devised by the brilliant physicist Erwin Schrödinger in 1935. It's important to note that this thought experiment is not about animal cruelty or harming a real cat. Instead, it's a powerful illustration of a fundamental concept in quantum mechanics called superposition, where particles can exist in multiple states at once. In the quantum world, particles like electrons can be in a state of superposition, existing in multiple places or states simultaneously until observed. Schrödinger's cat challenges our understanding of reality and observation, making us question what we know about the nature of existence. So the next time you see a cat, remember this fascinating thought experiment and the mysteries it unveils about our universe. The world of quantum mechanics is as mysterious and vast as the universe itself, full of wonders waiting to be explored. And just like the stars, the answers to these questions are out there, waiting for us to discover them. Schrödinger's cat is a thought experiment, not a real one. It was proposed by the Austrian physicist Erwin Schrödinger in 1935 to illustrate the peculiarities of quantum mechanics. It was designed to highlight the bizarre implications of applying quantum mechanics, the theory governing the microscopic world, to everyday objects. Schrödinger wanted to show how the strange rules of quantum physics could lead to paradoxes when applied to larger systems. The experiment highlights the counterintuitive nature of quantum superposition. In the quantum realm, particles can exist in multiple states at once, a phenomenon known as superposition. This means that until we observe the system, it can be in a combination of all possible states. Here's the setup. A cat is placed in a sealed box with a device that links its fate to the quantum world. This device is connected to a mechanism that can release poison based on the behavior of a single quantum particle. This device contains a radioactive atom, which has a 50% chance of decaying in a given time. The decay of the atom is a random event, governed by the principles of quantum mechanics. If it decays, the poison is released, killing the cat. The decay triggers a Geiger counter, which in turn activates a hammer that breaks a vial of poison. If not, the cat survives. Until the box is opened and the cat is observed, it is considered to be both alive and dead simultaneously, a superposition of states. In the quantum realm, particles like atoms don't exist in definite states like decayed or not decayed until observed. This means that until we actually measure or observe these particles, they exist in a state of uncertainty. They are not in one specific state, but rather in a combination of all possible states. Instead, they exist in a superposition of states, a blend of possibilities. This superposition is a fundamental concept in quantum mechanics, where particles can be in multiple states at once. It's a strange and counterintuitive idea, but it's been confirmed by numerous experiments. It's like flipping a coin. It's both heads and tails until it lands. Imagine a coin spinning in the air. While it's spinning, it doesn't have a definite outcome. It's only when it lands that we see it as either heads or tails. Similarly, quantum particles remain in a superposition until they are observed. In Schrödinger's cat, the radioactive atom is in superposition. This famous thought experiment by Erwin Schrödinger illustrates the concept of superposition in a more tangible way. The atom can be both decayed and undecayed at the same time. It's both decayed and undecayed simultaneously. This duality continues until an observation is made. The act of measuring or observing the atom forces it to choose one state, either decayed or undecayed. This means the cat, linked to the atom state, is also in superposition, both alive and dead until we open the box. The cat's fate is intertwined with the state of the atom, making it a perfect example of quantum superposition on a macroscopic scale. Opening the box constitutes an observation, forcing the system to collapse into one state or the other. This act of observation is crucial in quantum mechanics as it determines the final state of the system. Until we look, the system remains in a state of uncertainty, existing in multiple states at once. Schrödinger's cat was partly a critique of the Copenhagen interpretation of quantum mechanics, championed by Niels Bohr. This interpretation embraced the probabilistic nature of quantum mechanics, suggesting that particles don't have definite properties until measured. Albert Einstein, a staunch critic of this view, famously argued God does not play dice with the universe. He believed quantum mechanics was incomplete, and hidden variables determined a particle's state all along. Schrödinger's cat was a way to illustrate the absurdity of applying quantum superposition to macroscopic objects. Section 5. Schrödinger's skepticism, a cat's tale. Schrödinger, like Einstein, was skeptical of the Copenhagen interpretation. The cat experiment was a way to highlight the apparent absurdity of superposition at a larger scale. He argued that a cat couldn't be both alive and dead. The experiment wasn't meant to be taken literally. It was a thought experiment, a tool to probe the philosophical implications of quantum mechanics. Schrödinger used the cat as a metaphor to highlight the strangeness of quantum superposition applied to everyday objects. Section 6. The Copenhagen interpretation. Embracing uncertainty. Despite the critiques, the Copenhagen interpretation remains a dominant interpretation of quantum mechanics. It posits that the act of observation collapses the wave function, forcing the system into a definite state. This interpretation doesn't mean consciousness is required for collapse. Any interaction with the environment can constitute an observation. It suggests that the quantum world is inherently probabilistic, with outcomes determined by chance. Section 7. Many worlds, many cats. An alternative to the Copenhagen interpretation is the many worlds interpretation. This theory suggests that every quantum measurement doesn't collapse the wave function, but creates a split in the universe. In this view, each outcome of a quantum event occurs in a separate, parallel universe. So, in one universe, the cat is alive, and in another, it's dead. This interpretation, while mind-boggling, avoids the issue of wave function collapse and maintains deterministic evolution. Section 8. Quantum mechanics and reality, a paradigm shift. Schrödinger's cat highlights a fundamental shift in how we understand reality. Quantum mechanics suggests that the world isn't deterministic, but probabilistic. The act of observation plays a crucial role, influencing the outcome of events. This doesn't mean our everyday experiences are invalid. Macroscopic objects like cats are governed by classical physics, where superposition effects are negligible. However, at the atomic and subatomic levels, quantum mechanics reigns supreme. Section 9. The power of prediction. Judging scientific theories. Scientific theories are judged by their ability to predict experimental results. Quantum mechanics, despite its strangeness, has passed every experimental test thrown its way. It's the foundation of modern technologies like lasers, transistors, and magnetic resonance imaging, or MRI. While interpretations like the Copenhagen or many worlds may differ in their philosophical implications, they all agree on the mathematical formalism of quantum mechanics. This formalism has proven incredibly accurate in predicting experimental outcomes, solidifying quantum mechanics as a cornerstone of modern physics. Section 10. Schrödinger's legacy, a cat that changed physics. Schrödinger's cat, though a thought experiment, continues to spark debate and inspire new research in quantum foundations. It serves as a potent reminder that the quantum world operates under vastly different rules than our everyday experience. The cat's tail encourages us to question our assumptions about reality. It highlights the power of thought experiments in probing the boundaries of our understanding. As we delve deeper into the quantum realm, we're constantly reminded that the universe is far stranger and more wondrous than we could have imagined.